All right, welcome back. Today, we're jumping headfirst into one of the absolute biggest questions in all of science. It's this deep, kind of frustrating disconnect that's right at the heart of modern physics. So yeah, let's get into it, a potential solution to one of physics' greatest riddles.
So, let me ask you this. What if the rules for the universe at its grandest scale, stars and galaxies, and the rules for the tiniest, weirdest quantum scale, what if they aren't actually different at all? What if they're both just shadows? Shadows being cast by some deeper, single reality we haven't seen yet. That's the wild idea we're exploring today.
For about a century now, physics has had this total split personality. On one side, you've got Einstein's masterpiece, general relativity. That's the rulebook for the big stuff. Planets, galaxies, the whole cosmos. It tells us space-time isn't just a background, it's a dynamic, stretchy fabric that gets warped by mass and energy. But then on the other side, you have quantum mechanics. This is the rulebook for the tiny world of atoms and particles, and it basically assumes the complete opposite, that space-time is just a static, flat, boring stage where quantum weirdness happens. So, which is it? You can't have both. They just don't play nice together. They are fundamentally at odds.
So how in the world do you fix a problem like that? Well, there's a fascinating new idea that says maybe we've been going about this all wrong. It's called the Conformal Emergent Reality Model. We'll just call it CERM. And it presents this really radical perspective. It says, hey, instead of trying to glue these two theories together, let's see if they both came from the same place. Yeah, so the whole approach isn't about smashing these two theories together and hoping they stick. It's not about patching up the cracks. CERM asks a totally different question. What if both general relativity and quantum mechanics are just emergent? What if they both bubble up from something much deeper, a sort of common ancestor? The key takeaway here is huge. We're not trying to build a bridge between two separate islands. We're trying to prove they were part of the same continent all along.
Okay, so this model is built on three main ideas, three foundational pillars. And the analogy is actually pretty simple. First, you've got the blueprint. This is a kind of pre-space-time structure. Then you've got the architect, a special field whose job it is to actually build reality from that blueprint. And finally, there's the rule, a fundamental rule of uncertainty that's literally built into the geometry of everything from the very start.
So let's dig into that blueprint first. It's called a conformal manifold. Now stick with me here. Think of it as this primordial geometric stuff that exists before space and time even pop into existence. The really key thing to grasp is that this manifold has a causal structure. It knows that A can cause B, but it has zero sense of scale. There are no rulers, no clocks, no kilograms. It's just a pure, dimensionless blueprint for a universe.
Okay, now for that fundamental rule. I know, the equation on screen looks a little intimidating, but the core idea behind it is just profound. CARMM introduces a brand new kind of uncertainty principle. It says that way back on that primordial blueprint, you simply cannot know both the when, what they call prototime, and the shape, the curvature of geometry, at the exact same moment. And this is the critical part. This isn't about our measuring tools being clumsy. It's a fundamental built-in fuzziness in the very fabric of reality.
Okay, so we've got our blueprint and we've got our fundamental rule. What's missing? The architect, the thing that actually does the building. In this model, that role is played by something called the omega field, and its whole job is to take that scale-free blueprint and use it to construct the two very different physical worlds we observe.
Let's look at how it builds the world of general relativity first. The omega field has two jobs, or two components. The first is its geometric component. This is the part that takes the blueprint and actually creates curvature in space, which, you guessed it, is gravity. The second part is the chronos component, and that's what generates the flow of what we experience as cosmic time. You put those two together, and out pops a dynamic, evolving spacetime. I mean, that's a perfect description of general relativity.
Okay, so what about the quantum mechanics side of things? Well, for this, the omega field uses that fundamental uncertainty we talked about. Remember that built-in fuzziness between the when and the shape? That seeds these tiny primordial fluctuations. And now, here's the really elegant part of this whole model. In the relatively low-energy universe that you and I live in, this new geometric uncertainty principle just naturally becomes the good old Heisenberg uncertainty principle. That is the bedrock of quantum mechanics. And just like that, you get a world built on probabilities and quantum fields.
So there you have it. Two distinct worlds, general relativity and quantum mechanics, both growing from the very same root. But what's the actual connection? What's the one concept that truly ties them together, that proves they're just two sides of the same coin?
Well, the answer, the bridge that connects everything, is a brand new idea: geometric entropy.
Now hold on. This is not the entropy you're probably thinking of from chemistry class. You know, the measure of messiness in a room. No. Geometric entropy is something totally different. It's a fundamental property of the structure of space-time itself. It's a measure of how complex the geometry is. To use that old analogy, it's not about how the actors are arranged on the stage. It's about how complex the stage itself is.
And this is where it all really clicks. This one idea, geometric entropy, acts completely differently depending on the scale. In the big, cosmic world of general relativity, it grows globally, irreversibly. And what does that give us? The arrow of time. It's the reason time only ever flows in one direction. But down in the tiny, weird world of quantum mechanics, that exact same geometric entropy behaves locally. It fluctuates, driven by that built-in uncertainty. And what does that give us? The very concepts of information and probability that define the quantum realm. It's one concept playing two different roles and unifying everything. It's just beautiful. So, after all of that, what does this new picture of reality actually look like? Well, it's a completely new way of seeing things, and it challenges some of the most basic ideas we have about how the universe works. Let's just recap the biggest shifts in thinking here. We used to think space-time was the fundamental stage of reality. CERN says, nope, it's an emergent property that gets built by that omega field. We used to think quantum mechanics was just a bizarre set of rules happening on that stage. CERN says that weirdness is actually a property of the stage itself. We just kind of accepted that time moves forward. CERN says the arrow of time isn't a given. It emerges naturally from how geometry evolves. And finally, we thought uncertainty was just a limit on our measurements. CERN flips that on its head and says uncertainty is a fundamental rock-solid property of geometry.
There's a great quote from Salman Akhtar, the author behind this model, that just sums it all up perfectly. He says, "In this framework, the stage and the actors of the universe are made of the same fundamental stuff." Think about that. The deep division we always saw between space-time, the container, and the particles within it, it just dissolves. They're all just different expressions of the same underlying geometry.
And that, of course, leaves us with one final, mind-bending question. If everything, space, time, even quantum chance itself, all of it emerges from geometry, then what is the geometry made of? What is the stuff that the blueprint itself is written on? That's definitely something to think about. All right, that's it for this one. Thanks for diving in with me, and I'll see you next time.